So multimedia data, multimedia retrieval, and then some applications that we will do in today's class. So if you can see here, the pie chart represents that Google is generating 72% of the total US video streams all over the world. So this is actually a huge amount of videos which Google is generating, and since the number of this kind of multimedia data is huge, so how to manage that data and how to retrieve the information from that data is a challenge. So internet traffic is increasing day by day because people are posting videos and so much videos on Twitter, Facebook, etc. On YouTube also 24 hours every videos are getting uploaded per minute. Flickr also, if you see, 5,000 images are getting uploaded per minute. In iTunes, more than 10 billion songs are getting downloaded. On Amazon, you have greater than 650,000 books offered and millions of Kindles sold. So more ebooks are generally offered than the print versions on Amazon. So basically this is the amount of multimedia data which we are dealing with, and that's why we need to take care of it, and we need to retrieve the relevant information properly if we have multimedia data. So in multimedia retrieval, you could have some sample task, like if you have a music or a video recording and you want to find out the copies of that music or video. So you want to find out what duplicate similar music exists. Similar music exists on internet. So that then it is multimedia retrieval, because input is video and output is also a video. And then the output is also maybe an image or anything else. So it could be multiple mediums. Then you could have a person, you could write the name of a person, and you could want all images or all videos concerning that person. For example, he is a very famous personality. For example, he is Narendra Modi. So you just type the name Narendra Modi on Google and you want the images of Narendra Modi or the videos of him. So that is basically multimedia IR, because text is your input and output is images or video. Then you could also write a keyword. You could also speak a keyword and you would want an audio and video containing that keyword. So that is also again multimedia IR. And finding a music in a similar style. For example, when you play a game of Antakshari, so what you do is you hum a particular song and some bits of that song, and you want that the contestant should give the complete song. Sing the complete song. So it's basically when you are giving some piece of music and translating it into a complete audio. So that's again multimedia IR. And then finding all books and newspaper articles, mentioning a keyword. So there is a keyword which you mention and you want to find out all the books and newspaper articles with that keyword. These are all multimedia IR tasks. And applications could be in personal media management. For example, in duplicate removal, if you want to remove the duplicates. Then forensic applications like illegal copies. And then social science research like finding people and objects on internet. So what is multimedia actually? So it is one or more mediums which are linked to each other. So for example, this image you see, this image is of a lion. So this image, if you see, this image is of a lion, and what, suppose you have been given this image as input, you give this input image as a query. What you want is a wildlife documentaries of lion as an output. So basically your input is your image and your output is a video which contains this wildlife documentary of lion. So how it is fetched actually at the back end, there will be a linking of this image to the word lion. That means it's the lion image. Some data will be associated with this image which will tell that this image is of a lion. And then those wildlife documentaries will also have some data attached with them which will say that these are the wildlife documentaries of a lion. So at the back end it will do a text to text search and see that which data of which image is matching with which data of which video, and then it will retrieve the relevant videos. So this is what is done in multimedia information retrieval. They are possibly interlinked. The images, audio, everything is interlinked with each other at the back end. So images are generally represented in a digital format. So we will see how they are represented later. So if you see here, this is also a multimedia query only, because you are given an image and this image is of an ancient Buddhist temple which is very famous, and what we have is an input image as a query, and what we want is a description of this image. That means if it's a very famous ancient Buddhist temple, then what was the name of the temple, who built it, in which year it was built, what is so special about this architecture. All this information what we want is the result of our query. So input is an image and output is a text, basically in this case. So this is again an example of multimedia information. So what do we do actually is at the back end it's a text to text search only. So for example, you type a text and you want the images. So those images are also having some anchor text or some caption associated with them. So that will tell that this image is of which which this image is image description. Basically it will tell that what is this image actually. So at the back end all the images will have some anchor text and caption, and what we will do is we will arrange these images as an index in an index form by these anchor texts. So whatever the anchor texts are, we will arrange them in an index form, and whenever a text comes, so we will match it with the indexes, and in which, with whatever index it matches, that corresponding image we retrieve and give it to the user as the answer to the query. So basically at the back end it's a text to text search only. These images have their anchor text and captions from which we locate, from which we identify that which image is a relevant image to our query. And we arrange those anchor text in the index form, and then we can do a search easily by means of text to text search. So as I told you that a conventional is a text to text search, query is also in a textual form, and document is also in the textual format. However, there could be many options for the query as well as for the document. For example, the query could be an image, it could be a location like the latitude, longitude, it could be a speech, it could be a sound, it could be a humming, it could be a motion. And the documents could also be text, video, images, speech, music, sketches in the form of a sketches, or in any other multimedia format. So actually, there could be several combinations possible between a query and a document. Conventional is text-to-text retrieval, but however, there could be other options also. For example, if you see here, this green dot tells us that this is a text-to-speech conversion. So it could be a case when you are, suppose you are typing terror attacks. This is a text on Google, and what you want is a CNN, IBN news which tells us about the terror attacks. Might be some recent terror attacks might have happened. So if you type terror attacks on Google, then it will give me the news pertaining to that. So it's basically a speech. News is basically a speech. So it's a text to speech conversion in that case. We can take another example also. Suppose in the case of Antakshari, we hum a piece of music and we get all similar music to that. So it's a sound to, it's basically a humming to music conversion, this dot, red dot. So it's basically a humming to music conversion because you are humming a piece of music and you want all similar music. Then other case could be like you roar like a lion. This is very rare actually. We have not done this till now. That suppose a person roars like a lion, then the search engine is intelligent enough to tell that this is a lion roar, this is the roar of a lion, and that means it is able to identify that this is information in this roar is the lion. And then it will associate the wildlife documentaries of lion with this one and retrieve the videos of that documentary and give it to the user. So basically it's a sound to video conversion. Like sound is of that of a lion roar and the video is the wildlife documentaries of lion. So at the back end you have to relate the two. The sound and the video you have to relate it through some text to text. Then only this sound to video conversion is possible. And there could be other possibilities also. For example, location conversion to videos. For example, you're going to a new place and you don't know anything about that place. So you type the latitude, longitude of that place on Google and you will get the images and the videos and the text information about that place. So it's basically a location to text conversion or a location to video conversion or a location to images conversion in that case. And there could be other options also. For example, this motion option. Query could be in the form of a motion also and it could retrieve videos also. How? Motion to video conversion. So basically suppose there are some famous dance steps of some piece of music. Some song became very famous, some actor acted in that song and some actor danced in that song very well that those dance steps also became very famous. So suppose a person is dancing like that, is imitating the dance steps of that hero and the video of that song comes. Just imitating the dance steps of that person makes us that the video of that song comes, so that the search engine is intelligent enough to recognize that these are the dance steps which are involved in that particular song and that particular song's video it is able to fetch. So this could also be possible in future. Actually these all things have not been covered till now, but these could be future options for doing multimedia information retrieval. Okay. So there are two challenges here in multimedia information retrieval. One is semantic gap and other is polysemy. So let us study them one by one. Semantic gap means suppose this is an image. So from this image you can gather that this is an image, human can gather this thing that this is an image which is celebrating the victory. The football players are there and they are celebrating the victory because they have their cup here. So it's basically that they are celebrating their victory of football players. But suppose you give this image to a search engine, it will not be able to understand this thing, that this is the emotions involved in this picture. There are certain emotions. People are happy here, so they are celebrating. But the search engine cannot understand this. Maximum what it can understand is the pixel distribution, the pixels with their spatial distribution. So if it will see this image, it will just see that there is a black background here because too many black pixels are here. So it will see, it will identify that there is a black background here, so maybe it is night. And the maximum it can identify is that there are some faces and there is a vase-like object, the trophy. The trophy and the faces and the night, maximum this it can recognize, but it cannot recognize the sentiments involved in this. So if you give this input as a input image as a query, then the search engine will not be able to retrieve that what this image says, and therefore it will not be able to retrieve the accurate set of relevant documents. Okay. The other problem is polysemy. So if you have an image here, then this image contains two things: the person here and then some background poles are there. So now suppose you give this image as a query, then the search engine will not be able to understand that you are interested in the similar if you are interested in the person's images or in the pole's similar images. You are giving the query as a person, or your query is this background pose. So actually, yeah. So what semantic gap means? Somebody is saying sentiment analysis is possible. Sentiment analysis is possible from the text, but is it possible from the images? That is also a research area actually. It's a research area these days. It's going on, but how much efficiency we have achieved in this, that is again a question mark, right? So then polysemy, what I was saying was that suppose you have this image, then if you give this image as an input to a search engine as a query, then the search engine will not be able to understand that you are interested in this person or you are interested in this background pose. Means what is the focus of your query? So search engine will not be able to understand. So search engine might retrieve the relevant documents for this person, but you might be interested in these poles. So it could be a confusion actually. The search engine will not understand what is the focus of your query because of multiple objects in your query. Okay. Then other problem could be that how to combine possibly conflicting evidence of two images similarity. So for example, one image is that of a car and other image is that of a book. Now this car and book have got different features in them. So car can have a model number, mileage, etc. And book can have an year of publishing, who was the publisher, who were the authors. So the features on which the car has and the features of book, they are totally different. So how can you compare a car and a book, because of they have a different set of features altogether. So comparing them on a common set of features, then only you will be able to understand whether the two images are equal or same or not. But if they have a different set of features altogether, then comparing them would be very difficult. So this is again another problem. And the other problem is that the query vectors, that means the query images are less and the database feature vectors are very much. So we have to do a linear scan through the database in order to give a response to a query. So this is the responsiveness problem, and the first one was, this one was fusion problem. So metadata. So what is a metadata? So metadata is a piece of information about a multimedia object. So as I said, there could be an image, there could be a video, and at the back end we store some metadata, some data about that image or the video. That data will help us identify that what are the relevant set of documents, what are the relevant set of images or videos. So this metadata basically describes the resources so that they can be indexed, classified, located, browsed and found. So basically it will attach some information to that image or to that video that will help that image or video to be identified as an answer to your query. So it will help in locating or browsing for that image or that video, or classifying that this particular text belongs to this particular video. So matching the two at the back end, a lot of data should be involved in the images or the video, that is called as metadata. And it also stores the technical information. For example, the data format of the image, the format of the image, JPEG, TIFF, or compression scheme, what compression scheme you have followed for compressing that image, that also will be maintained as a metadata of that image. And other resources such as the access rights. So every image is not accessible to all. Some images are restricted also. So the image metadata will contain the permissions information, that which users are allowed to access this, and the location also. So where this image is currently located, that HTML link or that URL will also be present as a metadata of that image. and also the usage trails. For example, which section of a video has been watched how many times. So the frequency of, suppose there is a video, so the frequency of watching that video, that will also be stored as a metadata of that video. So how will that help? So if you have a frequency of video watching is also saved, then that will help, because when in future you will want an answer to your query, then you will test this video again and again, because it's a very popular video. So that means it might be the answer to your query also. So if you have the metadata that this is a very frequently accessed video, then you will associate that to the as the answer to your query very frequently, because it's a popular video. So it might be possible that it is an answer to your query also. So metadata is basically data about the multimedia object. So metadata gathering is difficult actually, because suppose you see this image. From this image you can find out that the title is Reconstruction of Colossus Computer, but the creator Suzanne Little or Tommy Flowers or Tony Sale, you do not know. Actually it depends upon your human knowledge, that how much knowledge you can gather about the creator, that will give you the exact metadata. If you do not have the complete and correct knowledge, then the metadata will be ambiguous actually. So comprehensive metadata is complex because you have to have a user created metadata. It's a human created metadata, so it is expensive and it's basically subjected to the human interpretations, human knowledge. So gathering metadata is difficult. At the back end we have always a text to text search, so it is called as a piggyback retrieval. So as I told you that the query could be in this several mediums and the document could also be in several mediums, but at the back end we always boil everything down to a text to text search. So query will also be a text, and at the back end documents will also be a text, and they will be matched, and then finally it will be retrieved. So so if it's even if the sound, if the query is a sound and what you require as an answer is a video, then also at the back end sound will also convert to text, video will also convert to text, and it will be a text to text, and it will be a text to text matching basically. So this is called as a piggyback retrieval. So because I told you that metadata gathering is very difficult, so that's why we proceed for a content based information retrieval. So content based multimedia information retrieval, how does it work? Suppose you have an image. This is an image of a polar bear in an icy background. So what it does is, instead of gathering the metadata about this polar bear and then finding out that which is the and then matching it with the metadata of the document images also, we do the other way around. So what we do is, we have this image, so we break it up into visual terms. So suppose this is an image, so it contains a polar bear. So this polar bear is one visual term. So we segment the image basically, and the icy background, we consider this as another visual term. So visual terms are also called as patches or blob tokens. Patches or blob tokens. So what we do here is, the image we break it up into different segments. Those segments are representing some these are called as visual terms or patches or blob tokens. Now, similar to the query, we break it up into terms and then we add those terms in the dictionary. Similar to that, we have done that. This is a multimedia image, so we have converted it into visual terms, broken up into visual terms, and add each of the visual terms in a dictionary. And then each visual terms postings list will contain the images which contain that particular visual term, similar to the posting list of a query term. So the posting list of a query term in text-based retrieval used to contain the documents which contain that term. Here it is the posting list which contains the images of that visual term, containing that visual term. So if this is a polar bear visual term, so it will contain in the posting list of this polar bear's visual term, there will be all images of polar bear only. And in the visual term which has this icy background, the posting list of that visual term will contain all the images of icy background only. Now once you have the two postings list generated, you will take the common images. That means those have the polar bear also and those have the icy background also. Those images you will take and that you will retrieve as an answer to your query. Okay, so this is called as content based retrieval. So instead of breaking up into terms, you are breaking up into visual terms, and the rest of the process is same basically. So what I am saying is that you have to figure out that which are the visual terms, and then you have to figure out the postings list, and then in that postings list the images should be of that visual term only. So first of all you should know what is that visual term, isn't it? So this is a polar bear. So how you annotate that this is a polar bear? So then only you will be able to find out these images of polar bear, right, in the postings list. So how do we annotate? So suppose you have this water, you have the grass, you have water here, you have grass here, you have trees here. Now how do you identify which is what? You just have some visual terms. Let us say you have three visual terms here, one of water, other of grass, and third of trees. How do you annotate it? That it is a water, it is a grass, it is a tree. So it is done by machine translation. So how do you align the keywords to the visual terms? That is done by machine translation. So there are different models for this, like probabilistic models are there, maximum entropy models, joint and conditional probabilities, and support vector machines. So what do is we, with each visual term, we associate a keyword. So how do we associate a keyword? We will find out what are the possibilities. For example, if you take this water visual term, suppose you take this visual term of water. Now you associate, you want to know that what is it? It is a water, it's a grass, or a tree. So you have three possibilities. It could be water, it could be grass, it could be trees. So what you do is you calculate the probability of translation of this visual term into water, into grass, and into trees. And then whichever probability is highest, that is the correct annotation of this visual term. So that is the formula. This is the formula. What it is doing is the same thing which I just explained, that you will convert this, you will calculate the probability of this visual term into each and every annotation. And then whatever is the highest, that will be the correct annotation. So we use some training data and annotations, and then probability of that word given that unseen image I. So this is your unseen image I, and this is the probability of that word grass or trees or water given the image of that particular, given that image, that input image, this image. Given this image, the probability of this, given this image, given this unseen image, visual term, then what is the probability of conversion to water, grass, or tree? Yeah, so one student is asking that how do we know that there is water, grass, and trees only? Some annotations, initial annotations you have to start with. So some initial set of annotations you will have to have. Some collection you will have to have. Then the correct identification that you will do by your machine translation models. But initially you have to have some annotations with you. Like some possibilities you should have. From that you can find out the best possibility. So the procedure says that you have a set of training images. The procedure says that you have a set of training images. You have some images. You segment those images into different segments, and those segments are basically nothing but the visual terms. So like you had the image of the polar bear, so you segment it into polar bear and icy background. So these is called as the visual terms. Okay. Now you link each of these objects that are the visual terms with their keywords. So you annotate the visual terms with the key terms, with the correct annotations. You annotate the visual terms now, and the objects, that means the visual terms, along with the keywords, along with the annotations, you maintain in an image object library. You maintain in a repository. That repository is called as an image object library. So each visual term along with its annotation, that is present in the image object library. So this is for the training set. So now once you have the training set ready, now whenever a testing image comes and you want to identify that what is the correct annotation for that testing image, so you segment it and create visual terms. So through object recognition, you segment this testing image also and create the visual terms for that, for the segments. And now for each of the visual terms you want to find out the correct annotation, so you will refer in the image object library and you will compare the visual term with the visual terms which are already present as a part of a training images, and then you will see which visual term matches which visual term, and then when you find a match, that visual term's annotation is the annotation of this visual term also. Okay, so this is done, this is called as an automated image annotation. So what do we do here is that you have, so the process here is that you segment the images into the visual terms. So you extract and quantize the features for the segments. So basically you are trying to extract here the visual terms only, and some visual terms might be similar to each other, so you cluster them together. So basically the first and second step is the segmenting of the image into different segments, and then some segments which are very similar to each other, you cluster them together in a one cluster only, and that is the final creation of a visual term. So that is the final creation of a visual term or a patch or a blob token. So this is how after clustering, after this step, you are able to generate the visual terms. Now once you have the visual terms ready with you, you analyze the correspondence between the different keywords and these visual terms, and then annotate the images by discovering the hidden semantics. So you analyze the correlations between the keywords and the blob tokens, and then you discover the hidden semantics that this visual term corresponds to which annotation. So what I was explaining is So quantization we will not study in detail because it's a phenomena which is more related to electronics people. Quantization is a phenomena which you might have studied in your digital logic, digital electronics. How to quantize. It's a standard phenomena basically. So this was what I was explaining. Suppose you have this image. These are the images. You segment the images into different features. So like this is a lion. So you have segmented this image into a lion segment, and then there's multiple grasses also. So this is one segment which is representing one type of grass. Is another segment. So like this you have created multiple segments in this image. If you see in the second image, this image also, you have segmented this lion as one segment and the remaining as another segment. Okay, so like this you do segmentation of the image. All the images you segment, and then whichever segments are similar to each other, those you cluster them into one visual term. So if you see here, this is the lion. In the first image also it is a lion, and the second image also it's a lion segment. Image segment is that of a lion. So you make these two segments, that is this lion and this lion, as belonging to one visual term only. Okay, so that's how you have created a visual term. So visual term could be a clustering of similar segments. So now once you have created this visual term V1, V2, now you have to annotate these visual terms. Visual terms or blob tokens or patches, one and the same thing. So now once you have created these visual terms after clustering, you have to annotate it. So our purpose is to find the correspondence between the blob tokens or the visual terms and the keywords. That is called as annotation. So suppose you have this image with you and you have extracted V1 and V3 as the visual terms. So how a visual term is connected to a cluster? One student is asking this question, how a visual term is connected to a cluster. So that's what I explained just now. So you have got these two segments of lion only. So this we know that these are the two, actually they are similar segments. If you see here, these are similar to each other. So that's why they are clustered into one visual term. Blob token is nothing but a visual term. So you see the similarity between the two segments. If the two images look similar to each other, then you will classify them into one visual term. Okay. Now once you have got the visual terms, now you have to annotate the visual terms. So let us say I have this image and this image has got two visual terms V1 and V3. V1 and V3. Now I want to annotate that V1 belongs to what and V3 belongs to what. So let us say I have got two annotations, tiger and grass. Now I want to associate that V1 is associated with tiger or with grass. So V1 is a tiger or a grass, that I want to know. So how to annotate this we will study now. So how to create the visual term, that is fine with you now. So what do we do here? We have a feature extraction through color, texture and shape. So one student was asking, how do we know that there is a similar visual term? So through color, texture and shape. So how do we generate a visual term? By k-means clustering. So through color, texture and shape, we will come to know that these two visual terms these two segments are similar to each other. So then we will use k-means clustering to find out the correct cluster, to generate the visual term. So then we will cluster them into one visual term. Let us say V1. Okay. So each cluster centroid will represent the visual term. So through the color, texture and shape, we will identify similar segments and then we will do k-means clustering to make it a cluster of a one visual term. Now once we have formulated the visual term, the purpose was that we want to find out the correct annotation. So what do we do? So what do? We use co-occurrence matrix for this. So suppose there are four visual terms and there are four annotations possible. So what do? Is we try to create a co-occurrence matrix using a training set of annotated images. So we try to use a co-occurrence matrix using a training set of annotated images. So we have got some annotations, we have got some visual terms, and now what we do is we calculate the probability of this visual term being converted into W1 and into W2, into W3 and W4. Now once we have all these probabilities, whatever probability is the highest, that is the correct annotation of that visual term. Okay. So we tend to annotate with higher frequency words. So whichever frequency is higher. So this 12 is highest here, so that means V1 will be 10 to be converted into W1. And a context is ignored. We need the joint probability model. So joint probability model means that V1 can be converted into W1 because it has got the highest probability. And then V2 will be converted into 40 because that has got the highest. V2 will be converted into W2 because that has got the highest probability, and so on. So again, one another So how do we get the probability values, one student is asking. So that we do using the IBM translation model. So you remember in the IBM translation model we had a foreign text and we had a foreign language and we had a English language, isn't it? And we used to find out we used to have a parallel corpus and we used to find out that which words are aligned to each other, like which foreign words are aligned to which English word. We used to find out that thing. So in the IBM translation models, we used to have a English sentence and we used to have a foreign sentence which are parallel to each other, and we used to find out which words in both are aligned to each other. Right? So the same concept we can use here also. What we can do here is the visual terms can be the foreign language terms, and the keywords or the annotations could be the English language words, and we are trying to analyze from we are trying to analyze the what possible alignments could be possible. So that means which visual term will be aligned to which annotation. So suppose I have got these visual terms with me and I have got these annotations with me, so I can use the IBM translation model in order to find out the correct alignment using the hidden structure. So what is the hidden structure? It basically gives me the probability that which alignment is more probable. And how do I get these probabilities? Using the parallel corpus. So using the parallel corpus, if the visual term was aligned to this particular keyword, if this visual term was aligned to sun more number of times in the parallel corpus, then using the hidden structure of the parallel corpus, we will be able to figure out that this probability is more, because with each iteration this alignment probability will increase because it is more number of times aligned in the parallel corpus. So then finally we will get to know that this visual term is matching with the annotation sun. So suppose in the case of a classical IBM translation model, your input was your foreign language and your output was basically your English language, and you used to find the correct alignment. The difference here is in the multimedia IR is that you use the same IBM classical machine translation model, but now you have the visual terms and you have the annotations, and you want to find out the correct alignment between the visual terms and the annotations. So it's kind of a bilingual corpus only. Like you used to have a parallel corpus in IBM machine translation model where there was a one English language and there was a foreign language, and here you have visual terms and annotations. Okay, you can use a similar concept here also. Now, how do we describe an image? So it is basically subjective interpretation always, because an image can mean different things to different people. For example, if I give an apple image, then somebody can say that it's an apple, somebody can say that it's a red ball. So it depends upon the perception of person. And we can have different features for different applications also. For example, I just explained that if you have a car and a book, then they will have an entirely different set of features. Like car will have a model number, mileage, and book will have year of publishing, authors, title, etc. So we cannot compare these two images because they have an entirely different set of features. Okay, and another thing is that color is also important for outdoor images, but not for X-rays, CT and MRI, because color is a feature which will be applicable not for X-rays, because X-rays are always black and white. So depending upon the images, depending upon your multimedia data, that certain features will hold, certain features will not be applicable for that particular image. So for example, motion features are important sometimes, for example in ultrasound, but in X-rays motion features is not important. So different systems will have the different features for different applications. That's what I mean to say. How do we represent a digital image? So suppose you have been given this image. Now how do you represent an image in our multimedia IR? So it's always a digital image. So what do? In the form of pixels we represent an image. So each image has got certain pixels in it, and those are each pixel will have a gray level value. So since it's a grayscale image, so all the values will be ranging from 0 to 255. 0 to 255 is the grayscale values. So 0 means black and 255 means white. And in between it is the intermediate levels of gray level. So if you take a portion of this image, let us say this image, I have zoomed this image here and shown you. So it is basically a combination of pixels. So there are 6 pixels in the rows and 6 pixels in the columns. So it's basically a 6 by 6 matrix. It's a 6 by 6 matrix which is representing some portion of the image, and there are different gray level values here. This is one gray level, this is white, this is something. So it is basically a conversion into a gray level. So if you see this portion of the digital image, I have converted into a pixel by pixel numbers, pixel by pixel representation. So the first pixel is having a gray level value of 145. The last pixel here in this row is having a value of 245 because it is very close to white. Because white has the value 255. So this is very close to white, so it is 245. And 0 means black. So always these ranges are always between 0 to 255. This thing you have to remember, that these ranges are always between 0 to 255. Okay, so each pixel will have its gray level value between 0 to 255 if it is a grayscale image. So that's why, so these numbers represent the gray level values of the each pixel of that image. So this is how we represent the digital image. So how do we create a histogram for a digital image? So we divide the gray levels into a different number of ranges. For example, I have divided the gray levels from 0 to 255 into a set of 8 ranges. So 32 each. So basically 0 to 31, that gray levels I have grouped as one bin. So I have created a different set of bins actually. So I have created 8 bins corresponding to ranges, corresponding to different ranges. So I have taken a size of each range as 32. So the gray level from 0 to 32, for that I have one bin. The gray level from 0 to 31 I have one bin. From 32 to 63 I have one bin, and 64 to 95 I have a third bin, and so on. So basically each bin contains 32 gray levels, right? And this will come in the x-axis. So why do we need histogram representation? That you will come to know. But please first of all let us understand that what is a histogram. Okay, so on the x-axis you have the gray level values ranges. So we have created 8 bins. Each bin is of 32 gray levels. And on the y-axis you have the number of pixels falling in that range. So between 0 to 31 you have how many pixels? That will be given by this y-axis. So for the second bin, that means for the gray levels between 32 to 63, how many are there? That will be given by this. So here it is telling you, this thing is telling you that in the sixth bin, this many pixels are present. So this is how we create a histogram. So what's a color histogram now? So that was a grayscale image, and we converted it into a histogram. Now suppose you want to convert it into a color histogram. You have a colored image here. Suppose this is your colored image and you want to convert it into a color histogram. So what you do is first identify all the colors in the image. So you have a gray color, you have a green color, you have a blue color, and so many colors are there. So each color represents one ball here, one circle here. So gray is representing one circle here, blue is representing one circle here, red is representing one circle here. So each color one circle. And the size of this circle, the size of this ball represents the number of pixels in that color. So since gray is many, there are many portion of this image is gray because too much cloudy weather. So the gray size ball, the gray ball size is more than the remaining pixels, than the remaining balls, because the gray ball is having more number of pixels than the other balls. Okay, so the size of the circle represents the number of pixels in that color. And then one important thing, the position of this circle. The position of this circle represents the color component, the color code. So whatever, how do we color code? First of all, let us see what is the color code. So white is represented in the RGB space by the code 255, 255, 255. So we have 3 components, red, green and blue, RGB, and for each of the 3 components we have some values, and the combination of these values will tell us that what is the color. So for white, all the 3 components have a value of 255. For black, all the 3 have a value of 000. And then intermediate colors have different sets of values for R, G and B. So now how do we represent this? So if you have 3 axes, red is represented on the x-axis, let us say, green is represented on the y-axis, and blue is represented on the z-axis. So each axis is on a range of 0 to 255. Is on a range of 0 to 255. So how do you represent RGB with a 255, 255, 255? That means the color white. So you have to have a place, a location where all the 3 become 255. So that will be the representation of white color. So how do you do it? So this white is at a position where red, green and blue all are at 255. So how do we plot it? So if you see here, this is the solution. So how do you plot for this white color? So since this is R is at the y-axis, green is at the x-axis and blue is at the z-axis, and all are beginning from 0 to 255. Okay, so this is also 255 and this is also 255. So now how do you represent white color? White color code is 255, 255, 255. So that means you have to go to here and then to here, because that will give me the red also 255 and then green also 255 and then blue also 255. You have to go to the Z axis. So this will give me, this point will actually give me the position where all three are 255. So this is why this circle is placed at this position. That's why that circle, white circle, is placed at this position. It is the position where all three are 255. And similarly, if you see black, black is 0, 0, 0. So that means it is here, because here it is all three are zeros. Red is also 0, blue is also 0, and green is also 0. So that's why we have placed that black dot at the position where all three are 0. Now if you see the representation for cyan, let us say it is 0, 255, 255. So red is 0, rest 2 are 255. So cyan color is this color. So how do you get the cyan color? This is the cyan dot. So it is basically red is 0. So there red is 0. So that's why it is coming here, and rest are 255, 255. So 255 here and 255 here. So it is coming here and red is 0. So that's why it is coming here like this. So like this you frame the positions. Now one important thing here is that you have to convert a 3D histogram into a 2D histogram also sometimes. So what do we do is, this is a 3D histogram what we did. This was a 3D histogram, but there could be another representation into a 2D histogram also. So what is a 2D histogram? You plot a separate histogram for each of the RGB components. So R, G and B, you plot 3 histograms here. So how do you plot here? You see in the red how many levels are there. You see in the red, so there 8 pixels are given to you. So you see for each of these, for all the 8 pixels in the red component, how many different levels are there. So there are only 2 different levels, 0 and 255. So you plot on the x-axis the different set of levels, 0 and 255. And on the y-axis you plot the number of pixels falling in each gray level. So you see here 0, 1, this is 1, this is 2, this is 3, this is 4. So 4 pixels, so 4 here. So that means you will plot a bar, you will plot just a bar graph which is at a height of 4. And then for 255 also 4 pixels are there, so 4. Like this. Now you see for the green component also there are only 2 different levels, 0 and 255. 0 and 255. So, and there are how many pixels for 0? 4 pixels again. So you plot for 4, you plot a chart like this, and for 255 also 4, so you plot like this. Then you see for blue component, again there are only 2 different levels, 0 and 255, and again 0 is having 4 pixels and 255 is having 4 pixels. So that's why you get this kind of a 2D histogram for all the 3 components. So what you have to see is for each of the 3 components, you have to see how many pixels fall in which level. So first of all, you have to see what are the levels. There are only 2 different levels here, 0 and 255. Then you have to see how many pixels are falling in each level, and that will be the plot for that particular red color. Then, so how do we know 4 pixels? One student is asking, because you see that 0 is contained in 4 pixels only. The red value for the red value for 0 is only for 4 pixels. This pixel, this pixel, this pixel, this pixel. So only 4 pixels are having the red value as 0. That's why we have plotted for number of pixels falling in the 0 value for red component is 4, and for 255 also it is 4. Similarly you do for green, and similarly you do for blue. Okay, but can you tell me what is the major disadvantage of this conversion into 2D histogram? What is the major disadvantage here? The major disadvantage here is that we have lost the information actually. We have converted from a joint probability distribution to a marginal probability distribution. Because in the 3D histogram we had a joint distribution. Because in the 3D histogram we were able to tell that these 3 are forming the white color. We used to know that this RGB is 255, 255, 255. So we used to know that this is the joint probability of existence, that RGB, if all 3 are 255, then only I can say that it is white. But in this case we only know the number of pixels falling in each level in each of the components. So for R we know that the number of pixels falling in 0 level is 4, but we do not know which are those pixels. For G also we do not know which are the pixels which are falling in 0, and for B also, blue also, we do not know which are the pixels which are falling in 0. So suppose I want to find out whether a black pixel exists or not. So I will see that the RGB for black is 0, 0, 0, but from this 2D histogram I cannot identify that the black pixel is present in this image or not, because it will just say that R also contains 1 pixel which has a red component value of 0, G also contains 1 pixel which has a green component value of 0, and B also. But it does not say that collectively they are having, that one pixel only is having all the three values as 0. It will not tell you that only one pixel is having the collective value as 0 for all three. It will tell that individually there are certain pixels which are having, there are 4 pixels which are having the red value as 0, but which are those 4 pixels? It will not be able to tell. So if it was able to tell me that the first pixel is that pixel which is having a value of 0 for the red component, and if the second graph was able to tell me that the first pixel is the pixel which is having the green value also as 0, and the third graph was able to tell me that the first pixel is the pixel which is having the blue value also as 0, then only I can say that since the first pixel is the pixel which is having all the three as 0, then it is a black pixel. That means it's a black pixel. But just by seeing these probabilities, just by seeing these individual graphs, I cannot find out that there is the existence of a black pixel or a white pixel or any other pixel, because it needs a joint probability distribution. I want to tell that RGB collectively hold a value of 0 for it to be black. Okay. So if I want to identify a black pixel, I should be able to tell that RGB are all zeros for that pixel only. Then only I can tell that that pixel is a black pixel. But from this graph, that information is lost actually. So for your exams point of view, you need to understand how to translate a 3D histogram into a 2D histogram. So please understand this thing. So how do we create a color histogram? We create a histogram with a bin for each color, and then we initialize the bin counter equal to 0. So for each pixel in the image, we will increment the bin counter corresponding to the pixel color. So we will see that which color pixel is coming, and then we have the corresponding bins. So we will increment the bin counter for that particular pixel color, and that's why in the end, when you have scanned all the pixels of the image, you will get for each and every color, you will get the number of pixels in that color. So this is how you create the color histogram. So what is the assumption in creating a histogram? You have the assumption that if two images share the similar colors, then their content is also similar. So that means if the number of pixels falling in each color for two images is same. Suppose there are two colors in this image and there are two colors in this image, and the number of pixels falling in the first color and in the second color for both the images is same. That means the pixel distribution is same. That means the number of pixels, basically the pixel number for the first color, let us say this is blue color and this is red color, and the second image also contains blue color and red color, and there are 10 pixels of blue and 10 pixels of red in the first image, and there are 10 pixels of blue and 10 pixels of red in the second image also. So this is the first image and this is the second image. Okay, so now I can say that these two images are same. Just by seeing their histograms and just by seeing the number of pixels in each color, I can say that these two images are same. This is our assumption, but this is not always correct. Why and in which case it will not be always correct? Because if you see, suppose this is a sunset image and it has got two colors, yellow and red, let us say. So there is another sunset image which has also got yellow and red and similar number of pixels in yellow and red. So I can say this is also sunset image, similar for here also. But suppose you see this frog image. So if you see this frog image, suppose it also contains red and yellow only, and the number of pixels in red and yellow is also same, then I cannot say that this frog image is equal to the sunset image. Why I cannot say? But because the number of pixels are matching in each color. Let us say there was red and yellow for sunset also and red and yellow for the frog image also, and the number of pixels also are same in each color. Then according to the histogram method, we have to say that these two images are same. But actually this assumption is wrong because the pixel distribution may vary. The number of pixels in red and yellow might be same, but they might be distributed differently in both the images. So the spatial distribution of the pixels also matters. So since we are not considering the spatial distribution of pixels in both the images, we just see the histogram and the number of pixels in each color. So we can say that these images are equal. We have to say this thing according to the histogram method. But it is not a very efficient method because it does not consider the low level, it does not consider high level features. High level features means the spatial distribution, the pixel distribution. So here the distribution is done differently, here it is done differently, even though the number of pixels in each color is the same. So that we are not considering. So there is a loss of information here because we are considering only low level features. Low level features as in the number of pixels in each color. We are considering only that low level features. High level features could be the spatial distribution of pixels. So this is a major disadvantage here. So I am just giving you an example of this frog image and the sunset image. You just assume that they have got equal number of colors and equal number of pixels in each color. But then also they are not same because their pixel distribution is different. So don't go by the literal image that there is a no yellow in this frog and in the sunset there is a yellow. Just assume that if there are two images which have got the same number of colors and the number of pixels in each color is also same, but then also their spatial distribution could be different. Okay. Then how do we compare the two images using the histogram method? So one student was asking me the question that what is the use of a histogram? So the use of a histogram is to compare the two images between the query and the database and find out which is the relevant database image. How do we do it? That